Okay, in this video, I want to continue on talking about significant figures. We talked about significant figures and precision and accuracy in the last video. Here, we want to talk about the different rules for significant figures, okay? You understand, hopefully, what accuracy and precision are. Generally, we're going to be dealing with significant figures. That's the poor man's version of precision, essentially. So rule number one, I think there's 5. Rule number 1, all non-zero digits are significant. All zeros that are bracketed, I mean, that bracketed means you have non-zero digits to the left and or to the right. All zeros bracketed by non-zero digits are significant. All leading zeros are not significant, so zeros to the left of the number, okay? All trailing zeros are always a problem. I'm not saying it's significant or not, but they're a problem. So, quiz time. How many significant figures are there in each of the following? Okay. First one, everybody and his mother says 5. Why? Because there's no non-zeros digits there. They are all significant. So the 1, the 6, the 3, the 8, the 7 are all significant. So 5. The second one, 3. The zeros in the front are leading zeros. Leading zeros are never significant. Okay. And the last one, there's 4. The zero between the 2 and the 9 is bracketed by the 2 and the 9. How many significant figures in each of these? The first one there's 6. Trailing zeros are ambiguous, right? I mean, I could make an argument that the first one has 6. I can make the argument that it has 7, has 8, has 9, okay? But we can go by, I call them the chemistry rules. I mean, nobody would, I think most people would agree that there's 6. I mean, I can make the argument that there is 9. Are those trailing zeros significant or not, okay? It really comes down to the following. I am 250 pounds. I was at the doctor's this morning. I got on a scale, it said 250 pounds. Does that mean it was 250, or was it actually 249 and I just rounded it to 250? Or was it 252 and I rounded it to 250? Or is it actually 250? It's a, I think most people would agree if I put a 0 after that, like for the second one here, that there would be 9. Okay? That dot at the end fixes. Decimal points fix trailing zeros. Decimal points do not fix leading zeros that you saw on the last slide. Trailing zeros do not, or decimal points do not fix leading zeros. They fix trailing zeros. We have we have these 3 zeros here are significant because of the decimal point has fixed it, okay? So the chemistry rule would say you have 6 for the first one, you have 9 for the second one, and we can go by the chemistry rule. I'm not going to quibble about this. The last one, these zeros here are leading zeros. A decimal point does not fix the leading zeros. It does fix these, okay? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 for the last one. The reason why I'm saying it's ambiguous is if I write the following, I weigh 250. Is that a decimal point or is that a period? And that's why I think it's ambiguous. I mean, you have to get it out of context. If you just write down a number and throw a dot at the end of it, you have to get the meaning out of context. So just to look at a number, I would say those first two, in all good consciousness, those first two to me are both ambiguous. But we can go by the chemistry rule where the first one will be 6, the second one will be 9. All digits are significant when expressed in standard scientific notation. That's how you get away from first one being 6, but I say it's ambiguous, and the second one being 9 because it's the decimal point fixes trailing zeros. you know, is that a decimal point? Is that a period? If you want to, if you're just not sure, if you need to definitely make sure that you have the correct number of significant figures, you put it into scientific notation, right? In scientific notation, trailing zeros are significant. Okay, so for the first one, there is 7, because the 1, the 2, the trailing zeros there are significant. The 6 that you see in the exponent has nothing to do with, is not significant. That's just if you have scientific notation, when you have the exponent, all the exponent's doing is moving decimal point left and right. So that's not changing any of the significant figures. So the first one is 7. Second one is 3. The third one is 2 significant figures, and 250 is ambiguous. If you want 250 with 3 significant figures, you have to write it with 2.50 times 10 to the 2. There's no way around it. Counting numbers are, this is rule number 3. Counting numbers are infinitely precise. Constants are infinitely precise. So if you have 10 plants in the experiment, it's not 10 plus or minus something. You have either 10 plants, or you have 9 plants, or you have 8 plants, or whatever. You can count them, right? If you have a formula, right, like the circumference of a circle is 2 pi r. The 2 and the pi are infinitely precise. It's not 2, one significant figure. It's 2.000. It's not approximately 2. It's exactly 2. Right, 2.000, that's infinitely precise. And pi is infinitely precise. It's 3.141592, blah, 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 blah. All those numbers are infinitely precise. All right, now here's where it comes into play, where you actually have to do something. The other ones are just knowledge based. This one you have to do something. When you add or subtract, same rule. When you add or subtract, what you do is you go back to what you did a long time ago, line up columns. When you're in grade school, you know, is given to you as 1.27527 plus 203.67. How did you do that in grade school? You lined up the columns, right? You write it so the decimal points line up, okay? And when you do that, so here the decimal points line up, right? The 1 is infinitely precise. The 2 here is infinitely precise. The 7 here is infinitely precise. The 5 is infinitely precise. The 2 is exactly 2. The 7 is exactly 7. This 0 is not exactly 0. It's about 0, right? It could be a little bit more than 0. It could be a little less than 0, and you would still write the same thing. So that's where our precision ends with that first number. Similarly, for the second number, 203.67, the 2, the 0, the 3, the 6 are exactly those numbers. The 7 is approximately 7. So the precision ends here. Okay, it doesn't matter that you know exactly 7, because even though this guy is exactly 7, this number here is completely unknown. We have no idea what this number is at all. Right, so you can add it to 7 all you want, but you don't care. Right, so what you do is you put those numbers one on top of the other, draw a line like I did here, which shows where the precision ends for the least one. Right, even though this guy has the second number that you're adding has only 5 significant figures. The first number has 7 significant figures. The second one is less precise because it's measured to the 100th place. The first number is more precise because it's measured to the 10,000, 100,000, the millionth place. Okay, so the second one has less significant figures. The first one has more significant figures, but the first one is more precise because it's measured better. It's measured to the millionth place, whereas the second number is measured to the 100th place. So these green numbers here, these green numbers are unknown, okay? These numbers here are completely unknown. The 5 is approximately a 5, right? But we know that it's a little bit more than a 5. Why is it at least 5? It's at least 5 because this is 5. And we're adding this much more to the 5. So we know that that 5 is actually more than 5, and so therefore we round up. Okay, so we have to look at those green numbers and ask ourselves whether we need to round it up or not. If it was 204.945, if it's more than 5, you'll round it up. If it's less than 5, you would leave it alone. So if it was 94 5270, you round up. If it was not 0.944999, you would not round it up, okay? So the final answer here is 204.95. You can be sure that when you take your first test, you're going to have to look at whether you need to round it up or not, right? That will be something that will definitely be tested, okay? Significant rules, number 4, continued, adding and subtracting, but you have it written in scientific notation. And I have it written so that these two numbers, we got the 10 to the minus 5 and 10 to the minus 6, right? First thing you have to do is basically factor out, rewrite it so you can factor out the exponent, right? So you write both 10 to the minus 5 or write both 10 to the minus 6 and factor them out, okay? And then the rest of it will be here. And then you default to what we did on the last slide, okay? And again, you would have to round this one up because the green numbers here are larger than 5, right? So that would round up. This rule is hard to say. It's easy to do, right? You have to take the numbers and line them up. And whether you add or subtract, you do what you're told to do. You add them up or subtract them, whatever you need to do. And it's easy to see what you have to do. It's hard to put in words, okay? Multiplication and division is easy to put into words. This is rule number 5. The answer to how many significant figures it has is, here we have two numbers. The first one has 6 significant figures. The second one has 5 significant figures. Your answer will have 5 significant figures because 5 is less than 6, right? This 5 is less than 6. 5 significant figures here, 6 significant figures here. So your answer will have 5. So your answer is 259.73, and we do not round up because it's less than 5 there.